Okay, we're going to talk a little bit more about Laplace impedance and transfer functions, which we started to talk about the other day. Okay, so we introduced previously this notion of circuits as dynamic systems, which is to say that the voltages and currents are a function of time. Right, so I draw the distinction here on the top. I've got a dynamic circuit. On the bottom, I've got a static circuit. The difference here is that in the static circuit, at time t equal to 0, the currents and the voltages are all steady, whereas in the dynamic circuit, they're going to evolve over time. Okay. The relationship for my dynamic circuit is shown here, basically in the top, right? I got that by doing KVL. Solving for that equation, I'll solve for V sub C of t. V of t here is the input voltage, V over here, okay? All right, so we know that the solution V sub C of t of this differential equation has two pieces, the particular and the transient. And we know that the transient is always a series of exponentials of the form e to the negative t over tau. And they're always declining over time. Now, what we did in the last part of the course is we said, okay, if our inputs, so in this case, the v of t, if those are specifically sinusoidal, and they have the form a cosine omega t plus some angle phi, then what we could do is we could use phasor analysis. And that would get us to the steady state solution, but we ignored the transient. All right, so the whole thing that we did was we learned this notion of impedance. It allowed us to get away from writing differential equations. All right, the downside of that potentially is that we weren't getting ultimately the transient response, but we were getting for ourselves the steady state response. And we were doing it without having to do a differential equation. So we basically said we moved to the phasor domain or the frequency domain. Then we use the impedance relationships to find the phasors for the voltages and currents. And then we move those results back into the time domain. In other words, back into a function of t, right? Which is the way things really are in the real world, right? We represented them as phasors, did complex algebra, but then can move back to the true time domain signals. All right, now there are limitations to this concept of impedance, and I wanted to talk about that briefly. The first limitation of this concept is that it doesn't allow us to solve for the transient response, and that sines and cosines are the only sources that we are allowed to use. So if we have any other kind of input, we can't use it. It is very appropriate because if you had to do something like mesh or nodal and you had to write differential equations, it would become very, very tricky to do that in any kind of efficient way. All right, that definitely would be a real challenge. So the question that arises is what happens if I have other kinds of signals and transients other than, or what kinds if I have other kinds of signals and I did care about transients, okay? So the example I gave the other day, I said 5u of t. And so I'm talking about this input here could be one of these different signals. U of t, this guy here, 5e to the negative 3t. And again, I usually multiply these all by u of t to say that they're turned on at t equal to 0. U of t is the unit step, right? U of t is this function that is 1 for t greater than 0 and 0 for t less than 0. And it represents effectively a functional representation of pressing the on button to turn on the circuit, okay? All right, so we have this idea of, to try to get there, to try to generalize impedance, we made use of the, and I'm gonna just make a quick note here, the way that I did this the other day, I defined this to go from negative infinity to infinity. Turns out there's actually two ways to define it. One thing I'm going to define here is I should really call this, and I'm not going to get into the math of this, the bilateral Laplace transform. All right. You might have learned something different, and you'll talk more about Laplace transforms later, but we don't usually deal with this. We usually say, okay, if I take a function f of t and I apply this Laplace transform, I get a function f of s, okay? So what we do is the Laplace transform allows us to move from functions of time to functions of s. So from f of t to f of s. Now, as we're going to see, that s value can be related to frequency and allows us to convert our differential equations to algebraic equations and makes the solution process a lot simpler. All right, so we derived for ourselves last time for a couple of different functions. So I did basically for u of t, and I plugged it in here, and I found that the Laplace transform u of s was 1 over s. We did it for some other common functions. All right, so basically what we said is that for this particular function, if I take the Laplace transform, I get a function of s. I might call it, if I have u of t, I might say that I get a result u of s, which is equal to 1 over s. Similarly, for this guy here, for the exponential, all right, when I take the Laplace transform, I usually write that little fancy L and say the result that I get from taking the Laplace transform of e to the at u of t would be that I would get a function of s that I would write as 1 over s minus a. Similarly, what I said was if I take the derivative of a function for t greater than 0, so let's say I had a function f of t, all right? F of t, we say, has a Laplace transform in general that is f of s. That was basically what our definition here was, right? So if I have a function f of t and I take its Laplace transform, I get f of s. So if I do that, what we said the other day is if I take df by dt, the Laplace transform basically becomes s times f of s, okay? The implicit assumption here is that f of t equals 0 for t less than 0, all right? And that's always going to kind of be the case that we're going to use for any of these applications, okay? Basically what this says is anything with a d by dt basically gets replaced with an s. So if I had a d squared by dt squared, that would ultimately get replaced by ns squared, okay? So we talked through those examples the other day, and we showed how we could use this result. So basically, if I went around and did KVL in this particular circuit, right, and I had this input, v of t is 5e to the negative 3t, specifically for t greater than or equal to 0, right? That's basically saying that this is equal to 5e to the negative 3t u of t, like that. All right. So if I have that, what I can do is I could say, well, all right, I take the Laplace transform of both sides of this equation, okay? And I can then solve for the Laplace transform of the output, which in this case is the capacitor voltage V sub C. So if I take the Laplace transform of both sides of this, basically what I'm saying is that V of t is represented by its Laplace transform V of s, okay? On the other side, I say I have RC times the transform of d by dt of VC, which we say is S times V sub C of S. And then for the last term here, I have V sub C of t becomes V sub C of S. So the top is in the time domain. The bottom I have here is in the Laplace domain, okay? What I do is this is now an algebraic expression, and I rearrange this and say V sub C of S is equal to V of S divided by SRC plus 1. All right, just doing my algebra there to get down to that particular result. Now, what I did up here is I said, well, if I had my V of t equal to 5e to the negative 3t u of t, that becomes V of s equal to 5 over s plus 3. So what I do is I plug that in here, and I end up with the results that I have shown here, okay? Now, I wrote this a little bit differently. So I said V sub C of s, right? I call that the output because that's the thing that I'm solving for. It's the voltage across the capacitor. V of s is the source. So it's basically the input to the circuit that's causing the voltages and currents to appear. And so I write this thing like I've shown here, where I say my output is equal to something times the Laplace transform of my input, okay? The Laplace transform of the output is equal to something times the Laplace transform of the input. So what I did was I showed in the previous slide there, the Laplace transform of my input was 5 times s plus 3. So what we do is if I want to figure out what is the time domain voltage V sub C of t, I take the inverse Laplace transform of that result. which is shown here, A over SRC plus 1 plus B over S plus 3. And what you guys know is you go through the partial fractions approach and you figure out, okay, well, what is ultimately A and B, all right? And what you're going to find is that it equals this result here, right? If I go through the inverse Laplace transform. I'm not going to go through and determine numeric values for A and B. You could do that. It's not hard, all right? But that's something I'm going to assume that you've seen before in differential equations, and I'm not going to focus heavily on it here. All right, so now let's say I have this particular, this led to basically some simplifications that we derived out the other day. All three of those results there are basically Ohm's law statements in the time domain for our three main components: capacitor, inductor, and resistor. Each one of those is in its own right a differential equation. So what I do is I can say, well, if I define for myself, that I of t has a Laplace transform, I of s, and V of t has a Laplace transform, V of s, then for each of these expressions here, I can write out for the capacitor, I of s equals SC times V of s. For the inductor, I can say V of s equals SL times I of s. And for the resistor, I can say V of s equals R times I of s. So in general, what I say is that for any component that I have where I know the Laplace transform of the current into the component, and I know the voltage across that component, what I see here is I have this relationship where I have V of s equals some impedance, Z, times I of s. And the impedances that I could have are, for a capacitor, 1 over SC. For an inductor, it's SL. And for a resistor, it's R. Now we can relate these, okay, as we will show, we can relate these to the impedance values that we had for sine waves, but effectively what we see is that these impedances are true for any input now, okay, and they can be used to solve for transients. But this S is just a different variable than we had before. Now, what we showed is that I can map these things into the different domains. And I went through this example the other day, and I said, okay, well, instead of writing out the differential equation, let's go to the Laplace domain. So I took the circuit that I had here, all right, and I mapped that over to the Laplace domain, and I replaced the resistor with its Laplace impedance, which is just simply R, and I replaced the capacitor with its Laplace impedance, which is just 1 over SC. And so I said, okay, well, if I want to solve for V sub C of S, the Laplace transform of the voltage across that capacitor, I use the voltage divider relationship, which is here, right? V of S, the input, times the impedance of the capacitor divided by R plus the impedance of the capacitor. Now what I'm doing here is I'm multiplying top and bottom by S sub C, which turns the function algebraically into this. And I call this specifically, this is a rational function of S. We're going to talk more about rational functions, but a rational function of S is basically a ratio of polynomials. All right, this guy is not a polynomial of S. This is. All right, we're going to see a number of examples of that as we go through. All right, now what we found here basically is this. We went through this last time and basically said if we look at what we wrote on the last line here, V sub C of S, the Laplace transform of the output is equal to the Laplace transform of the input divided by SRC plus 1. We said we can write it like this, right? Is I have an output, or the Laplace transform of an output, right, which is something that I'm solving for, is equal to something times the Laplace transform of the input, which is the current or voltage that I am supplying to the circuit. What we did is we termed this guy here the quote-unquote transfer function. And we usually refer to that and call it a function of S, often calling it h of S. Basically, what we have here is this notion of what I call a transfer function. All right, so what I'm doing here is I'm saying, okay, I can think of this circuit sort of abstractly as a system that is represented as a transfer function. And if I apply a particular input voltage or current to the circuit, I take the transform of that input and I multiply it by, so basically I'm saying the transform of the output. Transform of the output is equal to h of S times the transform of the input, okay? And that's what we did on the previous slides. Now, one thing that's often done is we don't tend to focus too much on taking Laplace transforms. There's ways we can get around that, but we do try to use this Laplace impedance to try to figure out the transfer function in different cases, okay? So, and we can solve for all sorts of different types of outputs, all right? So I want to look at a couple of different examples here. Let's say I have a voltage input and a voltage output, okay? So let's say the voltage that I'm concerned about here is, let's say it's V sub C of t, okay? So what I do is I map this to the Laplace domain. I don't even worry too much about what the input voltage is. I don't have to. I can just say the input voltage gets represented by its transform, V of S. I say this guy, resistor just becomes an R. The capacitor just becomes 1 over SC. And I say that the voltage across that is basically the transform of the capacitor voltage. All right, so what I do is I use the voltage divider relationship here, and I say that, well, V sub C of S is equal to what? It's equal to 1 over SC, the impedance here, over 1 over SC plus R times Laplace transform of the input. Just the voltage divider relationship, as if I was just doing this with regular impedances. And we said this guy becomes, if I simplify it, make it a rational function, it becomes 1 over SRC plus 1 times V of S. And we call this, in this particular case, our transfer function. So it's how I get from an input voltage to an output voltage. Now I could instead, if I said, well, what if what I was really interested in is my output is, okay, if I applied a particular voltage, I want to know what the current I of t is here. Well, if that's the case, I'd go through my general approach. I'd convert everything to the Laplace domain. And I'd say, over here I have V of S. Here I have R. Here I have 1 over SC again. And in this case, I'm interested in I of S, okay? So how would I solve for that? Well, if I of S is my output, I just use essentially Ohm's law for this thing, and I say I of S has to be equal to the input voltage V of S divided by the total impedance in the circuit. The total impedance in the circuit is R plus 1 over SC, like that. Now, again, I like these things, that's a correct answer, but I like these things to be rational functions of S, which means ratios of polynomials. So what I'm going to do here, again, is I'm going to multiply top and bottom by SC. Right? That's equivalent to multiplying by the number 1, because SC divided by SC is obviously equal to 1. That turns this into SC over SCR plus 1 V of S. So if this is the thing that I'm interested in, all right, then this is my transfer function, H of S. All right, what this transfer function is it's doing, and oftentimes we don't want to use the same name for the two different things. So I might call this, you know, I might give it a different name. I might call it Y of S, for instance. All right, I might give it a different name, but whatever I call it, whether I call it Y or X or whatever, doesn't really matter. What matters is it's the transfer function. It tells us in this case how we get from a voltage input to a current output. So it should look different, right? Because it's telling us something different. So the key takeaway we learned last time basically is in the Laplace domain, or sometimes the S domain, the output's always an algebraic function of the input. We take the Laplace transform our input voltage or current, create the transfer function, and then determine the Laplace transform of the output. If we want to go to the time domain, we can convert that Laplace transform of the output voltage or current to a time domain signal. Now, what's interesting about this is this result should collapse and relate itself to what I would have if I was talking about sine waves. Okay, sine waves remain a special case. So we've seen already, all right, that if what I was interested in was the capacitor voltage V sub c of t, if I took this over to the Laplace domain, I would get h of s as my transfer function, and that would be the relationship V sub c would be that h of s times whatever v of s is, okay? Well, let's say my input is v of t is equal to some amplitude v times cosine omega t, and let's again say that I applied that guy at t equal to 0, okay? Now, you may or may not remember this from your differential equations, but this guy has a Laplace transform v of s, which is equal to v over s squared plus omega squared, okay? And you can go back and you can derive that, but that's basically what it works out to be. And so what we end up with, and actually, sorry, it's actually for a cosine, it's s over s squared plus omega squared, and then I have the amplitude multiplying that, okay? So basically what it says is if I wanted to go to the time domain, I would get v sub c of s is equal to h of s times v of s, or plugging in what the transfer function is. The transfer function is s 1 over src plus 1. V of s is v times s over s squared plus omega squared, okay? Now, one of the things, if I take this result right here, all right, what I did was I took this guy here and I started to simplify it, okay? So what I did was I moved the RC out and I got it to this relationship right here, all right? Now, what I then did, all right, to try to take the Laplace transform is I said, okay, if I have s squared plus omega squared, I know that s squared plus omega squared, I could factor that as this, all right? Now, I'm not going to worry too much about the math. I just want to kind of show this result. S plus j omega times s minus j omega would equal this, okay? So what I did was I wrote this out here. And what you guys should know is that if I really wanted to solve this thing and figure out what the output voltage, and I should say V out in this particular case, what I'm really interested in is the capacitor voltage. All right, this guy would equal, you know, some sort of thing that I'm going to call, okay, I guess the way I did this is I called this guy K1, all right, K1 over S. I use partial fractions to write this guy like this, S plus 1 over RC plus K2 over S plus j omega. And without going through the result, what I find is that if you go through partial fractions, these two things here are always effectively going to be conjugates of each other, okay? Now, the important thing is I can go through this particular math if I wanted to go through this particular math, right? And what I find out when I do that and solve for these things, so I get this particular result here, right? When I go through this particular result, what I do is I find that K2 and K2 conjugate, they're always conjugates of each other. And what I fundamentally know is that this is going to give me an exponential. This is going to give me an exponential, and this is going to give me an exponential, okay? The important thing about this, right, these two particular ones right here, if I just looked at these, what I would see is that I get K2. So what we know is that 1 over S minus A is the Laplace transform of a time domain function, e to the AT. So if I have S minus j omega, that gives me K2 e to the j omega t. This guy would be K2 conjugate times e to the negative j omega t. Now, you know enough from working with Yawu in 2254, whether you realize it or not, and I'll add the transient in here too, e to the negative t over RC. You know enough from working with Yawu that Euler's identity tells me that this particular thing here is going to end up being 2 times the magnitude of K2 times the cosine of omega t plus whatever the angle of K2 is, all right? You would find out that that is the result, whereas I'm just saying in general that K2 is a complex number. Now, the interesting thing about this is if I go through the details of trying to solve this thing, all right, what I get is that K2 always works out to be this, and K2 conjugate always works out to be this. All right, now what that tells me here is that this particular result right here, this is what we've already referred to is the transient response, right? This is what we call the transient. And what we have over here, this is what we call our steady state response. All right, if I put those two things together, what I see is that my steady state response is basically V times the magnitude of the transfer function times cosine of omega t plus the angle of h of j omega. So this tells me an important result. It says that if my input is a sine wave, then my output is also going to be a sine wave. And the output, what I do is I take the magnitude of the transfer function at that particular frequency, and I evaluate it with S equal to j omega. Now that's interesting, all right? Because what we've seen already is if I looked at a simple example, right, where I have I of S, like if I looked at a capacitor, right? We said that for a capacitor where I equals C dV dt, we said that what we have is that I of S is SC times V of S, right? We had that particular result. This, we said the capacitor, the capacitor impedance, right, is 1 over SC in that particular case. So interestingly, if S equals j omega, notice that if I was talking about sine waves, it would become exactly what we remembered in that particular case for just simply sine waves. So this is interesting, right? Basically, the results become entirely consistent. Now, you're not going to need to go through that math again, but this is something that you're going to have to make use of in a number of different cases, right? So here's how we apply this, okay? So let's say in particular, again, that we're only interested in the steady state, okay? So let's go to the Laplace domain. So we go to the Laplace domain, we say that this circuit becomes represented by V of S. The input's V of S. This is R. This is 1 over SC. And I'm solving for V sub C of S. Now we've done this enough times that we can say V sub C of S is equal to 1 over SRC plus 1 times V sub C of S. Now let's just say, for sake of argument, that this guy here was 3 cosine 10t, okay? And we applied it at time t equal to 0. So we multiply that by u of t, okay? So let's call that our input, okay? And sorry, that should be not V sub C of S, but that should be V of S, okay? What this is telling us is that if I am interested in the steady state result, this here is the steady state result. So it tells me that essentially if I'm interested only in the steady state result V sub C of t would be equal to the magnitude of the input, the amplitude of the input, 3, times the value of the transfer function, h of j omega, right? So in this case, j10, right? H of j10, h of j10 times cosine of 10t plus the angle of h of j10. So what I'd have to do here is I would have to solve for, so my h of s is equal to 1 over src plus 1. I would basically solve for h of j10, plugging in s equal to j10. So this would become 1 over j10 rc plus 1. Let me write that somewhere else. Right? Let me write that down here. So I'll say h evaluated s equal to j10 is 1 over j10 rc plus 1. Let's just say in this particular circuit, let's say that R times C, I don't know, has a value of 1, right? If that's the case, this would become 1 over J10 plus 1. So if I were saying to myself, what's the magnitude of that? The magnitude of H of J10 would be simply 1 over the square root of 10 squared plus 1. Right? So that would, right, the magnitude of that would be 1 over the square root of 101. And the angle, h of j10, right, if you evaluated that, would be negative arctan of 10, okay? Not particularly hard to sort of solve for that, and I could plug this in. Now, that's a result that you will have to make use of in the homework. And we're going to use that, we're going to expand on that value a lot more as we go through the next couple of lectures. And I'm going to stop there.